Alright, in this video, we introduce the Fourier series. And Fourier series are based on a very wild assumption that any well-behaved periodic functions can be represented as a linear combination of sines and cosines. And the Fourier series has lots of practical applications, and also it eventually provided a lot of foundational notions in modern mathematics. So let's start. First, we introduce the notion of periodic functions. So we say a function f of x is periodic if, so this means if there exists some positive real number such that f of x plus t is equal to f of x for all x, which is in the domain of the function. In this case, we say this real number t is a period of f of x. And we can see that if t is a period, then 2t, 3t, 4t, and so on, any integer multiple of t is also a period. They are all periods of the same function. And the smallest non-zero period is called the fundamental period. Let's see an example. For each natural number n, cosine nx and sine nx, these functions have a period of 2 pi. So 2 pi is a period for all these functions. And for each of these functions, we have the fundamental period of 2 pi over n. So in fact, so let's consider this cosine function here. So cosine, let's say f of x is cosine nx, then f of x plus 2 pi is cosine n times x plus 2 pi. And if we expand this, we have cosine nx plus 2n pi, which is equal to cosine nx. So 2 pi is a period of this function. And if we substitute x plus 2 pi over n, then we have cosine n x plus 2 pi over n, and which is cosine nx plus 2 pi, which is equal to cosine nx. And if this constant is less than this value, then it's not, this equality doesn't hold. So 2 pi over n is the smallest period. Therefore, it is the fundamental period of this function. And the same applies to sine function. Okay, now let's define the Fourier series. So definition of Fourier series. That's easy. 1 over 2 is 0 plus n from 1 to infinity an cosine nx bn sine nx. So the series of this form where a0, a1, and so on, and b1, b2, and so on, they are real numbers. Well, usually real numbers. We may consider sometimes complex numbers, complex coefficients, but usually they are real numbers. But anyway, so any series of this form is called a Fourier series. Here, this 1/2, this factor may look a little bit strange compared to other terms, but this is for just for convenience reasons, which will become apparent later. And as you can see, since cosine of nx and sine of nx, they have a period of 2 pi. So the entire series here, if this defines any function, then this has a period of 2 pi. So as such, we may consider if this defines a function, then we can only consider this function on this domain, either from negative pi to pi, closed interval, or from 0 to 2 pi. Either is fine, or maybe we can use something else as long as the length of this interval is 2 pi. Anything is okay, but usually we use either this or this. Oh, by the way, this x is of course a real variable. Okay, this x. Okay, next, suppose we have a function f of x defined on an interval between, let's say, 0 to 2 pi. And if this function can be expressed in terms of a Fourier series, so that is this, an cosine nx, bn sine nx. Then we say this, the right hand side is the Fourier, or maybe we should say a Fourier series, Fourier expansion of the function f of x. Because we're not sure if this representation as a Fourier series is unique or not. For the moment, let's say a Fourier expansion, not that Fourier expansion. Here, one important question is, if we given this function f of x, and if we know that it can be expanded as a Fourier series like this, then how can we determine those coefficients? And so that's the next question. So let's find out. But before that, let us note some of the fundamental properties of these sine and cosine functions. First of all, if we integrate the product cosine nx times cosine mx dx from 0 to 2 pi, then this is equal to pi times Kronecker's delta, mn. So this is Kronecker's delta. In case you forgot, Kronecker's delta. So this is delta mn is equal to 1 if m is equal to n. Otherwise, it's 0. Okay, so if this n and m are equal, then this integral is equal to pi. Otherwise, it's 0. And similarly, for the sine function, sine nx sine mx dx is equal to the same, pi times Kronecker's delta mn. And finally, 2 pi, the product between sine and cosine. This is always 0. And you should check that. So just use some trigonometric formulas and identities and calculate this integral and show that these indeed hold. If you have studied linear algebra, this may look like these functions cosine x and cosine 2x and so on, and also sine x, sine 2x, and so on, they behave like the orthogonal basis set, right? So if they are equal, then this is 1, and otherwise they are orthogonal, so they kind of they don't overlap. So using these properties, we can determine the coefficients in this Fourier expansion. So that is, if we multiply both sides of this by, say, cosine of mx, then integrate from 0 to 2 pi, then we have, so 0 to 2 pi f of x and cosine mx dx. So the left-hand side will be this, and the right-hand side will be all these multiplied by cosine mx. Okay, but everything will be 0 according to these properties, except when cosine nx, so this n is equal to m. So in that case, the result is pi. Okay, so the result is pi, and in that case, Kronecker's delta is 1, so we have 1 here times, and the coefficient is here, that this an should be am because n is equal to m, so am is left here. Okay, and this also applies when m is equal to 0. Okay, so this is 0, 1, 2, and so on. So you should notice that if m is equal to 0, then that is cosine 0, which is just 1. And if you integrate this, just cosine times 1 from 0 to 2 pi, then it will be just 0. And same for this one. And the only term that is left is this one. So we integrate this constant from 0 to 2 pi, and we get just 1 over 2 times a0 times 2 pi. That is just pi times a0, which is just this, okay, with m equal to 0. Okay, so that's fine. And we do the same thing by multiplying both sides by sine mx. And then we have pi times bm for m equal to 1, 2, 3, and so on. So from this, we can determine the values of these coefficients. That is, am is equal to 1 over pi and the integral 2 pi f x cosine mx dx, and bm is equal to this. And m from 0, 1, 2, and so on, and m from 1, 2, and so on. And these coefficients, am and bm, are called Fourier coefficients. And by the way, this interval of integration, they can be from negative pi to pi. It doesn't matter as long as the period is 2 pi. All right, so far we have assumed that the function f of x can be represented by a Fourier expansion, this. Okay, now forget about this, and whether the function can be expressed as a Fourier series or not, it doesn't matter, but we can just define these coefficients, okay, irrespective of the possibility of the representation of f of x as a Fourier expansion, okay. So we don't care for now. And then using these coefficients, we can define the Fourier series, okay. So a0, and from 1 to infinity, an cosine nx and bn sine nx. So this is a Fourier series defined by these coefficients of f of x. And we do not know if this is actually equal to the original f of x. We don't know. But we can at least formally define this Fourier series. So this is how we define the Fourier series of f of x. Okay, and we also write f is, let's say, let's call it somehow related to this Fourier series. Okay, this Fourier series is defined based on this function through these coefficients. And the fundamental question in the theory of Fourier series is that whether this tilde is actually equal or not. And if this can be made equal, then under what conditions this equality holds? So these are the fundamental questions in the theory of Fourier series, which we will explore in this and later videos. Okay, let me repeat the questions, fundamental questions. So under what conditions does this series, Fourier series, converge? So convergence. And the next question is, under what conditions is this Fourier series actually equal to the function on which it is based? Okay, so these two are fundamental questions, and there are actually multiple ways to answer these. And anyway, for the rigorous discussion of Fourier series, we do need Lebesgue integral or measure theory, but I do not require this. Instead, sometimes I just resort to non-rigorous explanations, and we just try as far as we can get without the use of Lebesgue integral. That being said, let me just introduce a theorem and the sufficient condition for this equality approved by Carlson in 1966. So, okay, here's a theorem. Let f be a function that is measurable. I do not explain what this means, but when you study Lebesgue integral, then you will know. Measurable on the interval between 0 and 2 pi, and that is L2 integrable, which means i.e. The integral of this function squared dx is convergent. Okay, so L2 integrable means this holds. Okay, then the Fourier series S of f converges to the function f of x almost everywhere. Okay, so there are some terms which may not be familiar. Almost everywhere. This is actually a technical term, and which I do not explain. So it may not converge everywhere on this interval, but almost everywhere. So it has a precise meaning, but that's left for your further studies. But anyway, that's all for this video, and in the next video and after the next several videos, and we will explain more details about the Fourier series. See you later. Alright, in this video we study the so-called heat equation a little bit and see how the Fourier series arises naturally from the solution of this equation. So let's start. So here's the problem. First, consider a unit circle, that is the circle of radius 1 in some unit, and take any point on this circle. So this circle is made of some kind of wire that transmits heat. And any point on this circle, let's say P, can be measured by the distance from this point A. So let's say X. So this X, since this is a unit circle, this X corresponds to the angle between A and P. So this is X radian. And our problem is to find the temperature at any point, at any time. So let's say U of T and X represent the temperature of each point. And given the initial condition, at time equal to 0, the distribution of the temperature is given by this function f of x. So this is a known function. And it is known that this distribution of temperature follows the following heat equation. That is gamma, which is heat capacity per unit length of this wire, partial derivative of u with respect to time. This is proportional to the second derivative of u with respect to x, where kappa here is another constant. That's the thermal conductivity via cross-section of the wire. And both gamma and kappa, they are positive constants. By solving this heat equation, we can find this function, the distribution of the temperature at any point and at any time. Since this system is circular, it is natural to assume that this distribution of temperature is a periodic function with respect to the variable x. So that is at any point in time, x plus 2 pi is equal to u of t and x, because x plus 2 pi and x actually represents the same point. So this is x, and if you add 2 pi to this, then we get the same point. So we should have this periodicity of this function. From now on, we set gamma and kappa equal to 1. This is always possible by taking some appropriate unit. So instead of meters, we may use inches and so on. So by doing that, we can just set to this value. So this heat equation is simplified, apparently simplified to this partial differential equation. Well, we don't explain how to solve this equation, but it is possible to solve this. If you are interested in how to solve it, study the method of separation of variables. Okay, so by using the method of separation of variables, we can find that solutions of these partial differential equations are given by this. E exponential of negative n squared times t times cosine n x, or exponential of negative n squared times t times sine n x, where n is any constant. Although we do not show how we obtain these solutions, but it's easy to verify that these are indeed the solutions of this equation. For example, let's pick this one. And if you differentiate this with respect to t, this one, t appears only in this factor. So we have negative n squared exponential of this and cosine nt. And if you differentiate the same function twice with respect to x, n squared cosine nx. So x appears only in this factor. So if you differentiate cosine functions twice, you get negative cosine, but we have a scaling factor of x inside cosine, so that will come out twice. So that would be negative n squared and n squared t and cosine n of t, and so they are equal. Therefore, this is equal to this. That means we have this partial differential equation. Therefore, this is a solution. And you can do the same thing for this sine part. But we are not done yet, because this n, constant n, cannot be any value, because we have this condition. This is called periodic boundary condition. So n must be chosen so that this condition is satisfied. Actually, that's very easy. If we pick n from integers, then we can satisfy this periodic condition. Let's see it. So if n is an integer, then n squared t and cosine n x plus 2 pi is equal to cosine nx plus 2n pi. So this is equal to cosine nx. So the boundary condition is satisfied. The periodic boundary condition is satisfied. So as long as n is integer, actually it can be just positive integers, we have this is a solution. Either sine or cosine times exponential of negative n squared times t is a solution. Therefore, we just combine all of them, and the general solution is this, the linear combination of all these functions. And when n is equal to 0, we just have this term. And this term with n equal to 0, so it's a constant. So linear combination would be just constant plus all these functions from n equal to 1 to infinity, and exponential of negative n squared t, and some constant, because it's a linear combination, and cosine nx, and some constant, and sine nx. So this is the general solution of the heat equation. The next question is, we have an initial condition, right? That is given by, where is it? This one. So we have to choose the coefficient of that linear combination so that this initial condition is satisfied. So if we put t equal to 0, then we have this one, and this part will be just 1. And so it's an cosine nx, bn sine nx equals to f of x. So the coefficients a0, an, bn, they must be determined from this equation. This is the initial condition. So as you can see, this left-hand side is nothing but the Fourier series. All right, that's all for this video. See you later. Before going into the detail, let us determine some convention. By p 2 pi, we mean the set of, well, it may not be a set actually, but a collection of all functions with period of 2 pi. Okay, so all the functions we discuss will be elements of this set. Actually, in addition, we also assume that the functions in this set are continuous. Except for finitely many points. Except for finitely many points. So it can be discontinuous, but the point of discontinuity is at most finite. So not countably if infinite or uncountably infinite. It's just finitely many discontinuous points. And next we define R 2 pi 1. So this is another set of functions so that belong to p2 pi. So they have a period of 2 pi and number of discontinuous points is finite. And also they are also absolutely integrable. Okay, that means the integral from 0 to 2 pi of the absolute value of this function is finite. So this means absolutely integrable. Actually, it's Riemann integrable. What is what we mean? So this R stands for Riemann. So this means Riemann integrable. And similarly, we define R 2 pi 2. So this is again a subset of p2 pi, but in this case, the functions should be square integrable. So that means f squared is integrable. Okay, so this means square integrable. Well, if you already know Lebesgue integral, then you can just replace this with L1 integrable and this with L2 integrable. But in this lecture series, I do not assume the knowledge of Lebesgue integral, so we just stick to this notation with Riemann integrals. Now, actually, this R2 pi 1 and R2 pi 2, they are related. And in fact, if a function belongs to R2 pi 2, then that implies the function also belongs to R2 pi 1, not vice versa in general. And this can be proved by using the Cauchy-Schwarz inequality. Schwarz inequality. So that is if we have this integral, the absolute value of f of x. So this can be considered as this function times 1, and 1 is a constant function. So by applying the Cauchy-Schwarz inequality, this is less than or equal to the square root of the integral 2 pi and the square of the function dx times the square root of this 1 squared dx. Okay, so if this is finite, then this is finite. But this being finite indicates that the function belongs to R 2 pi 2. So this holds. Okay, let's see an example. Consider this function, f of x 1 over the absolute value of sine x to the power of alpha, where alpha is a constant that is positive. And we can show that if alpha is between 0 and 1, then f belongs to R 2 pi 1. So f is a periodic function and that is absolutely integrable. And if the value of alpha is between 0 and 1 half, then the function belongs to R 2 pi 2. So if alpha is greater than half and less than 1, then it belongs to R1 but not to R2. And you should know that this function is not continuous function on the interval between 0 and 2 pi, but there are some discontinuous points such as x equal to pi half, for example. But those discontinuous points are just finite. And actually, I think there are only 2 such points. So except for those points, this is continuous. And since we are taking this absolute value, and also this is periodic function, so we can consider this integral, let's say absolute value of f of x. As by symmetry, we can reduce this integral to from 0 to pi half and times 4 of this 1 over sine x to the power of alpha and dx. So this integral is reduced to this integral. Now we can express this function, this integral, in terms of the beta function. In case you have forgot, beta function is defined as this. Beta of p q is equal to integral from 0 to 1 x to the power of p minus 1 and x minus 1 minus x to the power of q minus 1 dx. And this p and q should be greater than 0. And by using the beta function, we can calculate some integrals involving sines and cosines. So sine to the power of a, theta, and cosine to the power of beta, d theta, can be expressed in terms of the beta function, this one. And I think we have shown this before somewhere. But anyway, I just list the formula. That's this integral becomes 1/2 times beta of a plus 1 over 2 and b plus 1 over 2 when alpha a and b are greater than -1. Now, using this formula, let's express this integral. Okay, so between 0 and pi half, sine x is positive, so we can just consider this. Okay, so let's see. So for integral sine x to the power of negative alpha, so this is negative alpha, and cosine x to the power of 0. There's no cosine here, so that's 1 dx. So this should be, apply this formula. So 1/2, so we have 4 here, so that should be 2 and beta function, and a is negative alpha, so that will be 1 minus alpha over 2, and b is 0, so that's 1 over 2. So that means as long as alpha is less than 1, so if alpha is less than 1, and of course assuming it's positive, then this integral is finite. And similarly, let's calculate the square of this function. So f of x squared. So that becomes this integral, and sine x to the power of negative 2 alpha here. So that becomes 2 beta and 1 minus 2 alpha and 1 over 2. So this is finite if this is positive. So that means alpha is less than 1/2. So actually alpha is assuming alpha is positive. So as long as this is satisfied, then this integral is finite. So it is square integrable. Otherwise, these integrals diverge, so we see that this conclusion is correct. In this video, we study Fourier cosine series and Fourier sine series. That is, if a function is an odd function, that is f of negative x is equal to negative f of x, then its Fourier series contains only the sine terms. That is something like this. So this is called a Fourier sine series. And when a function is an even function, that is when f of negative x is equal to f of x, then its Fourier series contains only the cosine terms and possibly some constant term. That is something like this. And this is called Fourier cosine series. So let's start. Let's consider a few more examples. Suppose f is a periodic function with a period of 2 pi that is defined by this: f of x is equal to x when x is between negative pi and pi. Okay, since this function is periodic, so what this means is this. So if you plot this between negative pi and pi, let's say this is negative pi and this is pi. This function is just x, so that is something like this. Okay, so not including this point, so this it looks like this. It's just a straight line, but it's a periodic function, so that means this same shape repeats again like this. So this would be, so the period is 2 pi, so this will be pi plus 2 pi, so this is 3 pi, and continue again and again. And same for the opposite side, so something like this, and something like this, and so on. So this would be negative 3 pi here. And as you can see, this is an odd function. That means f of negative x is equal to negative f of x. Okay, so let's say f of so some x is here, and take the negative value of this. So negative x and negative x, and the value of that is negative of this value. So that's what this means. So this is an odd function. And we can generally show that the Fourier series of an odd function involves only sines and there are no cosines. Let's see this for this example. Okay, so let's determine the Fourier coefficients. First, the coefficients of cosines. So this is 1 over pi integral from 0 to 2 pi, and f of x, cosine, and x. But this has a period of 2 pi, and cosine nx also has a period of 2 pi. So the product is also a periodic function with period of 2 pi. Therefore, we can just shift the interval here from negative pi to pi, and f of x and cosine nx dx. And now, f of x here is just x in this case, and x, and this is an odd function, and cosine nx is an even function. So the product is an odd function. Therefore, if we integrate from negative pi to pi, so this is the same amount of negative interval from 0 to negative pi and 0 to pi. So they're symmetric, but they just cancel each other. Therefore, the integral becomes 0. And for the coefficients of sines, similarly, we can just integrate from negative pi to pi and x and sine nx dx. Now this is an odd function, and sine nx is also an odd function. So their product is x times sine nx is an even function. So this is an even function. That means we can integrate, instead of negative pi to pi, we can just integrate from 0 to pi and multiply by 2. We have the same result because it's symmetric around the origin. And if you do this by, for example, integration by parts, and you get, you should get, let's see, what was it? This result, negative 1 to the power of n plus 1 times 2 over n. So, in summary, this function f of x, which is x, is its Fourier series is given by 2 times. So when n is 1, we have sine x over 1 and minus sine 2x over 2 plus sine 3x over 3 and so on. The general term is negative 1 to the power of n minus n plus 1 and of sine nx over n and so on. So that's it. And x is between negative pi and pi. And as you can see, there are only sine terms. There are no cosines involved. This is actually a general result for any odd functions. Any odd function can be expressed in terms of sine series. So if f is an odd function, that means f of negative x is negative f of x. It's an odd function. Then its Fourier series is given by the linear combination of sine functions. So this is called Fourier sine series in particular. In contrast, if f is an even function, if even means f of negative x is equal to f of x, so that means even function, then the Fourier series of f of an even function is given by in terms of cosines only. So that will be something like this. An cosine n of x. And this is called Fourier cosine series. Let's see an example. Consider f belonging to p 2 pi. So this is a periodic function with period of 2 pi. And that is defined by this 1 minus the absolute value of x over pi, where the absolute value of x is less than or equal to pi. But this is a periodic function, so this repeats beyond this range. Okay, so let's plot this. X, and let's say this is 0, and when x is equal to 0, it's 1. And when x becomes plus minus pi, then it reaches 0 here. So it looks like this triangle. Okay, and this is negative pi, and this is pi, and this is 1. And so this shape just repeats over and over like this. So this is pi, so this is 3 pi, this should be 5 pi, and so on. And same for this direction. And as you can see, this is an even function. So whatever the value here, let's say this is x, then the value at negative x. So negative x is somewhere here, and the value are the same. Okay, so this is an even function. So let's find the Fourier coefficients. And it's easy to see that the coefficients of sines are 0 by the symmetry argument. And a0 is just integral of this over this range interval, and you can see that it is actually 1. And more generally, let's say pi an is this integral f of x cosine nx dx. And since this is even and this is even, so the product is also even. So we can only consider the interval from 0 to pi and multiply by 2. Okay, and in this interval, the function is given by just x of 1 minus x over pi. And just brute force integration gives you, should give you this 2 over n squared of pi and 1 minus negative 1 to the power of n. And in this case, n is from 1 to 3 and so on. So when n is even, then this is 1. So it's 1 minus 1, and this becomes 0. So let's summarize the values of an. So that is equal to 1 when n is equal to 0. And it is equal to, when n is odd, then this is negative 1. So negative 1 times negative 1 is positive 1. So this becomes 2. 2 times 2, 4. 4 over n squared pi when n is odd. So 1, 3, 5, and so on. And otherwise, it's 0. 2, 4, 6, and so on. So that's it. So the final expression for the Fourier series cosine series is given by this 1 over 2, 4 over pi squared, and the first term 1 squared, and cosine 3x 3 squared, and so on. Next, consider we have a function g of x on this interval between 0 and pi. So it's not between negative pi and pi, but 0 and pi. Okay, only the positive side. Then, based on this function, let us define an odd function, fo of x, by following. So this is equal to g of x if x is between 0 and pi. Or it is equal to negative g of negative x when x is between negative pi and 0. Okay, and also we define this as a periodic function. So x plus 2n pi is defined to be f(o) of x, and when n is a natural number. Okay, and x is between negative pi and pi. Okay, so for this one, we use this definition. Okay, so in this way, we can define an odd periodic function with period of 2 pi. So here's what we are doing actually. So suppose we have a function defined on this interval. Okay, so let's say it can be any function like this. So this is g. Okay, g is originally defined on this interval, but now, so in this interval, we just use g of x as it is, as given. And for this, so from negative pi to pi, we just copy the mirror of this graph. So this should look like something like maybe like this. So we just make an image. So just rotate this graph around the origin to have this graph. Okay, so that is this part. Then for any integer natural number n, we define this one. Okay, so the value at here is defined by the value at this minus 2 pi. So it will be something like this one. So we just repeat this and this to let's see. So like this and this, and repeat to this side and this side. So in this way, we can construct an odd periodic function. Now for this fo, we can find the Fourier sine series. So fo of x may have the Fourier sine series, something like this, sine nx. Okay. But for this one, so for this one, the Fourier series of g of x, which is not really periodic to begin with, can be expressed in terms of sines, a linear combination of sines. And similarly, we can construct an even function, fe of x, based on g of x. So when x is between 0 and pi, we have gx, and when x is between negative pi and 0, we just define g of negative x. Okay. When x is negative here, then negative x is positive, so we can use this value. Okay, so it's symmetric around the y-axis. And also we can introduce the periodicity to n pi equal to fe of x when n is a natural number and x is between negative pi and pi. For this one, we can use these values. So if we have a function g of x defined on this interval between 0 and pi, then we can just make a symmetric mirror image around the y-axis to have something like this. And then we repeat the same pattern over and over, and so on to this side also. Then we have an even periodic function for which we can calculate the Fourier cosine series. That is fe of x. So Fourier cosine series would be something like 1 over 2a0 and an cosine nx. So when nx is between 0 and pi, then we can say g of x can be expressed, the Fourier series of g of x can be expressed in two ways. That is, first as a sine series, Fourier sine series, and sine nx, or as a cosine series. In two ways. All right, suppose we have the Fourier series of some function f, such as this one. In this video, we show that this Fourier series converges uniformly if the series of its coefficients, such as this one and this one, converge absolutely. So that means if this is positive infinity and if this is positive infinity, then this converges uniformly. And also that if this Fourier series converges uniformly, then it converges to the function f itself. So let's start. Now let us move on to the main topic of this video, that is the uniform convergence of Fourier series. So here's the lemma. Let f be a absolutely integrable function with period 2 pi with Fourier series satisfying this. And from 0 to infinity, an is convergent, and from 1 to infinity, bn is convergent. So a and bn are the Fourier coefficients of the Fourier series of this function. Okay. So if these two conditions are satisfied, then the Fourier series S of f converges uniformly. With respect to x, any x in real. Okay, and in particular, the Fourier series is continuous, is a continuous function. So let's prove it. Okay, first of all, let's prove. The Fourier series is this. 1 over 2a0 and the sum from n equal to 1 to infinity and an cosine nx and bn sine nx. So these an and bn come from this Fourier series. Okay. So now from based on this, consider this series 1 over 2 a0 plus n plus 1 infinity the absolute value of an plus the absolute value of bn. Okay, and cosine and sine, they are bounded between plus minus 1. So this an, absolute value of an, is greater than or equal to this term, and the absolute value of bn is greater than or equal to this term, bn times sine nx. So that means this is a dominating series of the Fourier series. Okay, and by the given conditions, this one, that means this series converges. So that means the dominated series, that is this Fourier series, converges. And And also note that this dominating series here does not depend on x. So that means the convergence of this Fourier series is a uniform convergence. So we have proved the first part. And so uniform convergence is proved. And about the continuity, we can see that all the terms in the Fourier series, they are continuous functions. So sines and cosines, they are continuous functions. So when a series converges uniformly, the continuity is inherited. Therefore, the Fourier series is a continuous function of x. And we are done. Okay, next number. If all the Fourier coefficients coefficients of a function, say f, which is periodic and absolutely integrable, all the free coefficients of 0, then so that means that is this integral, negative pi to pi, and f of x cosine n of x nx dx is equal to 0, and this one sine nx equal to 0. So all the coefficients are 0. Then fx0 is equal to 0, where x0 is any continuous point of f. Okay, f is not necessarily a continuous function, so it can be discontinuous at finitely many points. But as far as the continuous points are concerned, this should be equal to 0 if these are true. Okay. In addition, if in addition f is a continuous function, so if this function f happens to be a continuous function, it is a continuous function, then in this case f of x is identically equal to 0. So it's a constant function. So that means if we have some information about the Fourier coefficients, so in this case it's a very strong condition, all of them are all the coefficients are 0. In that case, we have some information, we can get some information about the function, the original function f at its continuous points. Okay, in that that is, it's always 0 at those continuous points. Okay, so let's prove this. First of all, this x0 is nothing special. So by shifting x0, let's see, x2, x minus x0, we can always set, without losing generality, if x0 should can be just 0. Okay, we may assume x0 is equal to 0. So there's no loss of generality here. Okay, so we prove by contradiction. Okay, so suppose f of 0 is not equal to 0. And in particular, let's assume it's positive. Okay, and we're assuming f is continuous at x equal to 0. Okay, so that means by the definition of continuity, since f of x is continuous at x equal to 0, this is by assumption. Okay, so there exists some delta that is positive, such that if x, actually this should be, maybe I should write x minus 0 is less than delta, then f of x minus f of 0 should be less than f0 of divided by 2. So this can be any real positive real number. So we, in particular, we just pick this positive number. Okay. So this is guaranteed if we assume f of 0 is positive. Okay. Now, by the triangle inequality, we have f of x, maybe f of 0 minus f of x is less than or equal to f of x minus f of 0. But from this is less than f0 over 2. So by rearranging this inequality, we have f of x absolute value is greater than f of 0 over 2. Now let us define a helper function. This is a bit technical, but it's helpful. So p of x is defined as 1 plus cosine x minus cosine delta. This delta is this delta, okay, same delta. And we are assuming that x is between negative and positive pi. Okay, assuming this, if x is less than or equal to delta, then cosine x is greater than or equal to cosine delta. That is because of the cosine function. Let's plot this cosine function. Cosine function is around, let's see. So cosine function looks like this. And let's say delta is here and negative delta is here. So if x is between plus minus delta, then cosine x is greater than cosine delta. So this holds. Okay, so this means 1 plus cosine x minus cosine delta is greater than or equal to 1. So that means by the definition of p of x, p of x is greater than or equal to 1. Okay, next, if x is greater than delta, or the less than negative delta, then that means cosine, wait a minute, first, negative 1 less than equal to cosine x, and that is less than cosine delta. So x is somewhere here. In this case, cosine delta is greater. Okay, so from this, we can see that if you add 1 and subtract cosine delta from everything here, then we have negative cosine delta and p of x less than 1. And of course, negative cosine delta is greater than negative 1. So that means the absolute value of p of x is less than 1. Okay, now let's consider the power of p of x. P of x to the power of k. This is up, so p of x is this one. So if we calculate the power of this function, then this is a polynomial of cosine x. Okay, so that means it contains powers of cosine x, something like this. Okay, and however, this cosine x to the power of k is a linear combination of some constant plus cosine x and cosine 2x up to cosine kx. So C0, C1, C2 up to Ck, there are some constants. We can always express powers of cosine x in terms of this linear combination. Okay, this can be easily proved by, for example, using mathematical induction and combined with some trigonometric identity. Now, to this equality, multiply both sides by f of x. And so f of x cosine to the power of k, then integrate over this interval, negative pi to pi. Okay, so this is c0 times f of x plus c1 cosine x times f of x, and so on. So all these integrals are 0 because of the assumption. So we are assuming all the Fourier coefficients are 0, so these are zeros. So this integral becomes 0. Now we split this interval into two parts. So this is equal to when x is between plus minus delta. So this part is just this part. And when x is greater, the absolute value of x is greater than delta. Maybe we can put here. Okay. Okay, for the first part, x is between plus minus delta, and we have seen that p of x is in this range. P of x is greater than 1, and also from this one, so x minus 0 is just x. Okay, so for this interval, we have this. Well, actually, since we are assuming that this delta is sufficiently small and we're assuming that f of 0 is positive, we can actually get rid of this modular sign, and we can assume that if x is small enough, then f of x is greater than f0 over 2. So we may assume this. So going back to this integral, so the first part becomes this greater than 2 and 1. So p to the power of k is greater than 1. So dx. Just a moment. So excuse me, this is not this, but x between plus minus delta, and the second term, just leave it as it is. So if we integrate this part, then we have integrate this part, we have f of 0 times delta plus x greater than delta, and f of x p of x to the power of k. Now let us evaluate this integral. Okay, so first of all, if x is in this range, so if x is between not 0 but delta and pi, then we have as we have seen before, in this case we have this. So p of x is bounded by 1. So that means f of x, p of x to the power of k, is dominated by f of x. Okay, so this is a dominating function. And furthermore, by assumption, f of x is absolutely integrable between plus minus pi, and of course it is absolutely integrable in this interval. So this is finite. And also, if we take the limit k going to infinity, and f of x and p of x to the power of k, since p of x is less than 1, this converges to 0. Okay, and when x is greater than delta. Okay, so we have a dominating function that is absolutely integrable, and this function converges to 0. That means this limit k going to infinity and this integral x greater than delta f of x p of x to the power of k dx. So we can swap the order of limit and integral by Arzeller's theorem. Okay, so we can swap the order, limit f of x p of x to the power of k dx. So Arzeller's theorem, and this is 0. So this limit is 0, so integral of 0 is 0. Okay, now, so we have this is equal to f0 of delta. And of course, we're assuming f of 0 is positive. This is by assumption. And delta is positive. And so, but this integral is less than 0. So that means we have 0 less than this, which is greater than 0. Okay, so this is a contradiction. And therefore, f of 0 cannot be positive. Cannot is not positive. And if we assume f of 0 is negative, and we can just swap the signs and do the same argument, this is also impossible. Therefore, and you should check that, therefore this must be equal to 0. And we are done. All right, now we are ready to prove the following important theorem. So suppose Fourier series of f converges if converges uniformly. Then S of f of x0 converges to f of x, where x0 is any continuous point. Of f of x. And in particular, in addition, if f of x is continuous, then we have f is equal to s of f. So f is equal to its Fourier series itself. Okay, let's prove this. Actually, the proof is not so difficult if we use that lemma we have just proved. So let us define g of x as the Fourier series of f. That is this: 0 and n from 1 to infinity, an cosine nx, and bn sine nx. And by assumption, this series converges uniformly. This series, Fourier series, converges uniformly. So that therefore, g of x is continuous everywhere. And also, termwise integration is allowed. And termwise integration is allowed. Okay, so let's take advantage of this. So from this, if we multiply both sides of this by cosine n and integrate between negative pi and positive pi, we have g of x cosine nx dx. So if we do this, we have pi an. And similarly, we just use the orthogonality of the cosine and sines. And similarly, if we multiply both sides by sine nx and integrate, we have pi bn. So this is because the termwise integral is okay to do. Okay, now we combine this with the Fourier coefficients of f. So by definition, we have this f of x times cosine nx dx equal to pi an. So this is how we defined an and bn to begin with. And sine dx. So by subtracting both sides, this and this and this and this, we have this. So f of x minus g of x times cosine nx dx equal to 0. So this minus this, the right hand side is 0, and also f of x minus g of x sine nx dx equal to 0. So we have this. But by the above lemma, so consider f minus g as one function. Then that means uh, f of x0 minus g of x0 is equal to 0, where x0 is a continuous point, is any continuous point of f minus g. So f minus g is just another function. Okay, so wherever f is continuous, g is always continuous. Wherever f is continuous, then we have f of x is equal to g of x, wherever f is continuous. So in particular, if f is continuous everywhere, then f is equal to g everywhere. And we are done. And the next theorem should be almost trivial by now. But anyway, let's write it down. Suppose f is a function that is absolutely integrable, and with Fourier coefficients an that is absolutely convergent, and bn also, then S of f, the Fourier series of f converges uniformly. And S of f of x is equal to f of x, where x is any continuous point of f. So I don't give the proof of this theorem, but you can just review what we have done in this video and just combine all the results, and I think it should be easy to prove. Okay, anyway, so let's see one example. That is this one. So if we calculate the Fourier series of this function, which we have dealt with before. This is, so before it was like the Fourier series of this function, so this was tilde here, was this cosine x over 1 squared plus cosine 3x over 3 squared, and so on. And x is between negative pi and pi. But now, if we apply this theorem, we can see that this is actually equal. So the Fourier series of this is equal to this function itself. To see this, the coefficients are this. So 1/2 and okay, 1/2. So this is A0. And A1 is 4 over pi squared, and A2 is 0, and A3 is 4 over pi squared and 3 squared, and so on. Okay, and the series of these coefficients is like this. So the sum, an. So let's consider this, and that is 1/2 4 over pi squared, 4 over pi squared, 3 squared, and so on. So that is 1 over 2 and 4 pi and 1, 3 squared, 5 squared, and so on. So this converges. Therefore, according to the theorem here, we have this equality. So therefore, this Fourier series is equal to the original function itself. And we're done. Okay, that's all for this video. See you later. Alright, in this video we studied the complex Fourier series that is of this form. So the index varies from negative infinity to positive infinity, and the coefficients are complex numbers in general. And here we have exponential of I, k, x, where I is the imaginary unit, of course, and x is a real variable. So let's start. First of all, let's compare this with the real Fourier series of this form, which we have been studying so far. K cosine kx and bk sine kx. So apart from being complex valued, this complex Fourier series is actually equivalent to this real complex series. Well, except for the coefficients being real or complex. That's because of this Euler's formula. As you know it, exponential of I kx, where k and x are real. This can be written as cosine of kx and I sine kx. So if you substitute this into this series, then you have something like this one by changing coefficients appropriately. Now, suppose we have a function f that belongs to r2 pi and 1. So that is a periodic function with period of 2 pi that is absolutely integrable. In this case, the complex Fourier coefficient ck is defined as 1 over 2 pi integral from negative pi and pi. So this can be 0 to 2 pi, but it's just a periodic function, so this is okay. And f of x, an exponential of negative I kx and dx. So this is not this negative sign. So rather than this positive exponent, we have negative exponent here. And so if we determine the coefficients in this way, then the complex Fourier series of this function f is this one. So let's write it as S of f, that is this sum, ck and exponential of ikx. So this kx, ck is this ckx, okay? So this one is this one. Okay, next, let's forget about this. So in this case, in the previous case, we assume that there exists a function f. And for this function, we determine the complex Fourier coefficients, okay? But now forget about this, and suppose a function is defined by this complex Fourier series. EIKX. And assume this belongs to R2 pi 1. And now let's multiply both sides by exponential of negative I m x, for example. So multiply both sides by this. Then on the left-hand side, we have f of x exponential of negative I m x. And on the right-hand side, we have this summation, ck exponential of I k minus m x. And let's integrate both sides from negative pi to pi. Negative pi to pi. Okay. Now on the right hand side, this function is, since we're assuming that this is absolutely integrable, we can apply Aljo's theorem and swap the order of integral and the sum. So we have, we can put this coefficient out, and exponential of I k minus m x dx. So what is this integral? We consider two separate cases. So case 1, when k is equal to m, then this integral becomes just, so this exponent becomes 0, so it's just 1 dx, that is 2 pi. And second case, when k is not equal to m, then in this case we have this integral I k minus m x dx. So we can just treat I k minus m as a constant. So it's I 1 over I k minus m. No, this is not 0, so it's okay to divide by this. And this k minus m x and negative pi. So this is equal to exponential of I k minus m pi minus I k minus m pi, which is equal to 0. So this one corresponds to, on the complex plane, so pi times integer, some integer, so k minus m is an integer. So we rotate this point 1 time, 2 times, 3 times, and so on by pi. So k minus m times in the counterclockwise. Okay, here we do the same thing but clockwise. But in either case, we always get the same number here on the complex plane. So this should be equal to 0. So let's go back to this integral. So this is equal to 2 pi if k is equal to m. Okay, and otherwise it's 0. So the only term that remains is when k is equal to m, so that is Cm. Okay, so this is the result. And as you can see, if you divide both sides by 2 pi, then we have the Fourier coefficient of this function that we defined here. Okay, let's consider an example. F of x equal to exponential of ix over 2 for x between negative pi and pi. And we're assuming this is a periodic function with a period of 2 pi. Okay, and so this looks like this. So if you consider the real part, that is cosine of x over 2, and the imaginary part is sine x over 2. So if you plot x versus this function, the real part is this one, cosine. So when x is equal to 0, that's 1. And when x is equal to, let's see, 2 pi, x is equal to pi, then it should be 0. Okay, let's see, this is pi, and it looks like this. And negative pi looks like this. Okay, and so this continues repeatedly. So we just copy this function to this range, like this, and like this, and so on. So this is the real part. And the imaginary part is sine x over 2, and when x is equal to 0, that's 0. And when x is equal to pi, that is this. So it should look like this. So if you repeat this, so if you shift this by 2 pi, you get something like this. And like this. So as you can see, the real part is continuous, but the imaginary part is not continuous. And let's calculate the Fourier coefficients. Ck, let's multiply by 2 pi, just for the sake of simplicity. And cosine, not cosine, it's exponential ix over 2 times exponential of negative ikx dx. So that is exponential of I x 1 over 2 minus k dx. And that is, what is it? 1 over I, 1 over 2 minus k, and exponential of I x 1 over 2 k, negative pi, and pi. And that is exponential of I pi minus negative I pi, this. And let's split this into, so I pi 1/2 times negative I k pi. And here we have I minus pi half times I plus I k pi. Okay, so this one, I pi half is equal to, that is I. And I negative, this one, I negative I pi half is equal to negative I. And exponential of negative I k pi is equal to what is it? It's pi, so -1. And if k is odd, then it's -1. If k is even, it's +1. So it's -I to the power of k. And this is actually equal to this one too. So substitute these values into here. We have 2 pi ck equal to 1 over I 1 over 2 minus k. And let's see, I. And this minus and -I. And this. So these negative signs cancel, and we have, so this I, they cancel, and we have 2, this, and 1 over 2 minus k. And let's see, so let's multiply both here and here by 2. We have 4, 1 minus 2k. So ck is this divided by 2 pi. We have 2 k and pi 1 minus 2k. So this is the Fourier coefficient. It's real. So after all, we have the Fourier series of this function as this 2 over pi and sum over k from -infinity to +infinity, and -1 to the power of k, 1 minus 2k, and exponential of ikx. Okay, next let's consider this partial complex Fourier series. K varying from -n to +n, and ck exponential of ikx. And use the Euler's formula to expand this exponential function into cosine and sine. And then we have this C0. So when k is equal to 0, we have just C0 because this is 1. And k from 1 to n. And so positive k and negative k, let's combine them together. And we have ck plus c minus k. And cosine kx. And the imaginary part, we have I and ck minus c minus k, and sine minus sine kx, because sine function is an odd function, so we have this negative sign here. And so if we define 1/2 a0 to be c0 and ak to be ck plus c minus k, and bk to be I ck minus c minus k, then we have this partial series as 1/2 a0 and from 1 to n, and ak cosine of kx and bk and sine of kx. So if we take the limit, assuming this converges, then we have the real Fourier series. So assuming this and this are all these coefficients ak and bk are real. Okay, so that can happen if these are complex conjugate of each other. Okay, so this is purely real, and this this will be purely imaginary. So multiplying by I, it becomes real. So basically, the complex Fourier series and real Fourier series, they are equivalent. Since the real and complex Fourier series are equivalent to each other, we can apply all the theorems that we have proved for the real Fourier series to the complex Fourier series. So I will list those theorems without proof, because the proof is essentially the same as the previous one for the real Fourier series. So first one, lemma, that is zero function. So assume the function is periodic and absolutely integrable. Then if the complex Fourier coefficient of that function is 0, negative ikx dx. If this is 0, then for all integers, of course, then f of x0 is equal to 0, where x0 is a continuous point. Continuous point means the point at which the function is continuous. Okay, and naturally, if f is a continuous function, then the function f is identically equal to 0, if this is true. And next theorem, if the complex Fourier series of f converges uniformly, then we have f equal to s of f. So the function f is equal to its complex Fourier series. So this is just like we have seen for the real Fourier series. And to see if the complex Fourier series converges uniformly or not, the following theorem is useful. So if we have a Fourier series such as this one, ikx, then if the series of the coefficient converges absolutely, then this Fourier series converges uniformly. So if this ck converges, so this means the coefficient converges absolutely, then this Fourier series converges absolutely. Uniformly. And just this is also just like the one we have proved for the real Fourier series. Okay, that's all for this video. See you later. Alright, the goal of this video is to prove that if a function f is piecewise smooth, then the Fourier series of that function converges uniformly to the function f. And the meaning of piecewise smooth is the following. First of all, let us denote by C2 pi m the set of functions of class Cm, that is m times continuously differentiable functions with period of 2 pi. And now we say f is piecewise smooth if f belongs to c2 pi 0. This means f is a continuous function, and f prime belongs to r2 pi 2, that is square integrable. And in this video, we only consider the complex Fourier series. That is, if f is given, its Fourier series is expressed as this, with possibly complex coefficients, kx, and the Fourier coefficients are defined by this formula. F of x exponential of negative ikx dx. All right, first thing we prove is Bessel's inequality. Bessel's inequality. That is, if f is square integrable, then 2 pi sum of the absolute value squared of the Fourier coefficients is less than or equal to this integral, the square modulus of this. Okay, let's prove this. First of all, let us define Sn of x as the partial sum of the Fourier series. That is, okay, from negative n to n, positive n. And ck exponential of ikx. And then, let's consider this integral. The modulus f of x minus Sn of x squared. Okay, now we are considering complex Fourier series. So this absolute value means the absolute value of a complex number. Okay, so this is equal to fx and Sn of x times the complex conjugate of this. So fx and Sn of x complex conjugate dx. Okay, and the complex conjugate over sum is sum of complex conjugate, or sum or difference. And if you just expand this, we have this times this, so we have f of x squared, absolute value squared, and the minus f of s, wait a minute, okay, f of x, Sn bar, and Sn of x, f bar, plus Sn squared, absolute value squared, dx. And now let's substitute this into here and here. Let's split the integral. And the next one, f of x, and sum of this minus n, and we are taking the complex conjugate of this, so that becomes ck bar minus ikx dx. And this part, that is ck exponential of ikx and f bar dx. And Let's write on the next line. So this is CKE plus K, and K prime might C K minus IKX dx. And if you expand this, you have something like this, and ck bar and exponential of ik minus I prime x dx. And as we have seen before, so this term, when integrated, becomes either 0 or 2 pi because of the orthogonality of this basis. And also, this times this becomes the Fourier coefficient, and this times this becomes the complex conjugate of the Fourier coefficients. So this becomes the first term unchanged, and the second term becomes, so we can swap the sum and the integral, and the sum becomes this. So ck bar, and integral of this times this is the ck, right? And similar for this one, and that is k is ck and ck bar, and this one it's ck minus n, k, and k from negative n to positive n, and this becomes oh wait a minute, so this is 2 pi is missing here, so if we integrate this we get 2 pi, and this one becomes 2 pi, and Kronecker delta k prime and k prime, but if you sum over k prime, then this becomes 1 when k prime is equal to 1. Otherwise, everything is 0, so we have 2 pi, and ck, this should be prime here, and ck bar. Okay, so one of them cancels this, and this becomes ck absolute value squared. But this left-hand side, to begin with, this integrand is always non-negative. Therefore, this is greater than or equal to 0. So this right-hand side must be also greater than or equal to 0. Therefore, we have this. Now, the left-hand side doesn't depend on n. The right-hand side, this is always positive, and if we take the limit and going to infinity, we have 2 pi and sum of k from negative infinity to positive infinity. Then the inequality still holds. Okay, so this is greater than or equal to this, and we have the desired result, and we are done. Now let us prove our main result. That is theorem. If f is a continuous function and f prime, its derivative, is square integrable, then the Fourier series of f converges uniformly to f. Here we use this double arrow to indicate that the convergence is uniform. Okay, let's prove this. First of all, let us express the Fourier series of the derivative f prime as this. K from negative infinity to positive infinity and gamma k and exponential of k I k x. And gamma k is, of course, the Fourier coefficient of f prime. Okay, so just in case, that's this. F prime of x and exponential of negative I kx dx. Okay, now we're assuming that f prime is square integrable. So that means this. Not infinity, to pi, and the absolute value of f prime squared is finite. And this is because f prime belongs to this class. Okay, now let's consider this one. So integrate this, the square of it, k from, it's implied that k varies from negative infinity to positive infinity. Okay, and consider this. Okay, if you expand this, by the way, this is complex number, so this is absolute value of complex number. That is this times its complex conjugate. And if you again use the orthogonality of these functions, then the result should be equal to the sum of gamma k absolute value squared times 2 pi. Now let's use the lemma we have just proved. And so this quantity here is less than or equal to this integral f prime and squared. And by assumption, this is finite. So that means this sum is finite. Okay, now let's calculate the Fourier coefficient ck of f. Okay, so this is by definition this f of x times exponential of negative I kx dx. Now we apply the, let's integrate by parts. So this becomes 1 over I k f of x e I kx and minus minus plus here I k f prime I kx. But this one, f is a periodic function with period of 2 pi, and so is this term. That means if we take the difference between the values at pi and negative pi, they have the same value because of the periodicity. So therefore, this will disappear. This will be just 0. So what's left is this one. But this part is the definition of the Fourier coefficient of f prime. So this is equal to 2 pi over ik gamma k. And of course, here we're assuming that c is not equal to 0. K is not equal to 0. Okay, so after all, we have ck equals to gamma k over I k. K is non-zero. Now let's consider the sum of ck, absolute value of ck, where k is non-zero. So this is equal to this. So 1 over k absolute value times absolute value of gamma k. And by using the Cauchy-Schwarz inequality, we have square root of sum of k squared and square root of sum of gamma k squared. So this is from Cauchy-Schwarz. But notice that this summation here converges, it's finite. And this summation here, we just show that it's finite, right? This is finite. Therefore, this is finite. That means the series of the Fourier coefficient of f is absolutely convergent. And that implies the Fourier series of f converges uniformly to f. And we are done. Now, the left-hand side doesn't depend on n. The right-hand side, this is always positive, and if we take the limit and going to infinity, we have 2 pi and sum of k from negative infinity to positive infinity. Then the inequality still holds. Okay, so this is greater than or equal to this, and we have the desired result, and we are done. All right, in this video, we study the collection of square integrable functions with period of 2 pi, and see that this can be regarded as a vector space with some appropriately defined vector addition and scalar multiplication. And we also define the norm in this space and also the inner product in this space, inner product between functions in this collection. So that in this way we can interpret this collection of functions as some kind of geometric object. Okay, to see that this collection of functions is a vector space over C, that is the set of complex numbers, we need to define addition and scalar multiplication. And let's say f and g are such functions in this set. Then we define f plus g by this equation, f of x plus g of x. So it's just the addition of the functional values. Okay, and let's say any alpha. In complex numbers, we define alpha f by this equation, alpha times f of x. And of course, x is any real number. Well, this is a periodic function, so we can limit this domain between negative pi to pi, but it doesn't matter much. Anyway, addition and scalar multiplication are thus defined. Now, in order to prove that this collection of functions is a vector space, we need to show the bunch of axioms, those that are these. First is this set is closed under vector addition, and the addition is commutative, and it's also associative, and there is some a zero element in the space. And for each element, there exists an additive inverse such that this holds. And also, scalar multiplication satisfies this closure condition, and this distribution of addition of scalars and distribution of addition of functions, and the existence of the multiplicative identity of the scalar, and the associativity of scalar multiplication. So these are pretty easy to show. So I don't prove all of them here, but only the first one, this one, closure of addition. Let's do that. Okay, so what we need to show is, assuming f and g are elements of this collection, then we show that f plus g is also an element of this collection. So to show this, we need to show this integral. So this f plus g is square integrable. So that means f of x plus g of x modulus squared dx is finite. So this is our goal. So let's do it. So we start from this, and since f of x and g of x, they are just complex numbers, so its modulus, to its modulus, we can apply the triangle inequality. So this is less than or equal to f of x modulus and g of x modulus everything squared. So this is by triangle inequality. And just expand this, and then we have f of x squared and g of x squared and 2f and g everything dx. Then split the integrals. And this one plus 2 f of x times g of x. Okay, now this one, f modulus and g modulus, they are just non-negative real numbers. Okay, so for non-negative real numbers, let's say for any a b that are positive or 0, we have the arithmetic mean is greater than or equal to the geometric mean, right? So let's say so if a is f modulus squared and b is g modulus squared, then this part is, so let's write this first, and so this part is less than or equal to the sum of these divided by 2. So 2 f of x squared plus g of x squared divided by 2. So this is the geometric mean, and this is the arithmetic mean of this and this. So these two will cancel, and we have f modulus squared here, and g modulus squared here and here. So let's combine them together, and we have this and this, g of x. So by assumption, this is finite and this is finite. Therefore, the total sum is finite. Therefore, f plus g belongs to this set. Therefore, this is closed under the vector addition, and we're done. And other axioms can be easily proved. For the details, please see my lecture notes. So now we know that the collection of functions r2 pi squared is a vector space. We can define the length of each vector by the L2 norm, or also known as mean square norm. Okay, suppose f is a function belonging to this space, then its norm, L2 norm, is defined as this. First, calculate the integral of the modulus of that function squared, and then square root. So this is called the L2 norm, or mean square norm. Well, if you compare this norm to the norm of the n-dimensional Euclidean space, a vector space, suppose, let's say x is something like this, 1, 2, and up to n. So this is n-dimensional vector. Its norm was defined as this. Its Euclidean norm was defined as this. So sum of I from 1 to n x1 xi squared, and take the sum and take the square root. So they are very similar. So instead of summation, we have integration here. Otherwise, it's all the same. So elements are squared here. And then after taking the sum or integral, we take the square root. So they are parallel to each other in a sense. And in this sum of n-dimensional vector, of course, there are n elements. Okay, but here in the integral, how many elements are there? Actually, there are infinitely many elements, right? Because this is an almost continuous function between negative pi and pi. So there are infinitely many points at which this functional value squared is calculated. So the dimension of this vector space of functions is actually infinity. So it's an infinite dimensional vector space. And any vector space equipped with a norm is called a normed vector space, or simply normed space. So our collection of functions, periodic functions, square integrable, this is a normed space. And remember the scalar product or dot product between vectors? We can define something similar for this space of functions. And that is called L2 inner product. Here we are considering complex valued functions here. So it's a little bit tricky. But anyway, so f comma g within brackets. So this is the inner product between f and g that is defined as this. The integral f of x and g of x conjugate, complex conjugate, dx. So this is called the L2 inner product. Well, we can define whatever we want as long as it makes sense. So does this inner product make sense? So what do we mean by that? So it means this integral is finite. So let's take the absolute value of this. This is a complex valued function, so the inner product may be any complex number. So let's take the modulus of that, and using this, this is equal to less than or equal to the integral of the modulus. So this is another manifestation of triangle inequality, actually. And so we can split the integrand into two parts. So the modulus of a product is the product of the moduli, right? So we can split this like this. But the modulus of the complex conjugate is just the same as the modulus of the original function, original complex number. So this is equal to f of x modulus and g of x modulus. Okay, again, using the fact that the arithmetic mean is greater than or equal to the geometric mean. So this is less than or equal to this f of x modulus squared plus g of x modulus squared over 2. Now, split the integrals. This is equal. And we have actually, so we have, let's use the norm notation. So by assumption, this is finite and this is finite. Therefore, the sum is finite. Therefore, this integral makes sense, and this inner product is well defined. And let's compare this inner product with the scalar product between ordinary vectors. So if we have two vectors, let's say x, x1 up to xn, and y, from y1 to yn. So they belong to real n-dimensional vector space, let's say. So the scalar product between these two vectors were defined as this, I from 1 to n, and xi, yi, and sum of this. Okay, so if you compare this with the inner product between two functions, then we take the product at each between each corresponding elements, and then take the sum. Here we take the product between functional values at each point within this range of integration, then integrate. So integration is just a sum in essence. So they are basically the same thing. The only essential difference is that this is finite and this is infinite. And also, if we consider complex n-dimensional vector space, then we define the scalar product as this. So xi and yi conjugate, complex conjugates. In that case, this is more similar to our definition of the inner product. So we can see that this inner product is a generalization of the scalar product between two vectors. And just like any other scalar products, we can prove the Cauchy-Schwarz inequality for this inner product. So if we have two functions, then we have this inequality. So the modulus of the inner product is less than or equal to the product of the norms of each of them. Okay, so the proof is an exercise. Okay, so this is called Cauchy-Schwarz inequality. And again, just like the usual scalar product, we have the following properties for the L2 inner product. That is, first, the norm squared is equal to the inner product uh, of the same function. And inner product between f and g, if we swap the order, g and f, that becomes the complex conjugate of that. And f1, f2 inner product with g is f1 g plus f2 g. So this is kind of a distributive law of inner product. And the same applies to the second component. So f inner product with g1 plus g2 is the inner product between f and g1 plus f1 g2. And also alpha is a complex number. So alpha is a complex number. It's a scalar. So alpha f times g is alpha f g. And f alpha g is alpha complex conjugate f of g. So all of these should be easy to prove. So they are almost trivial. So it's an exercise. If we use this inner product, the Fourier coefficient of a function f can be expressed very concisely. That is, so the Fourier coefficient ck of function f is just this. 1 over 2 pi and f and exponential of I kx. So to see this, just go back to the definition of this inner product. So that is this integral f of x, and the complex conjugate of this is exponential of negative I kx. So this is the Fourier coefficient ck of f. And the orthogonality of these functions, exponential of I n x, can be expressed as this. E to the power of I n x and e to the power of I m x is equal to 2 pi delta, so Kronecker's delta, n m. So just go back to the definition of this inner product. What this means is this. This e I n x, and the complex conjugate of this is e minus I mx dx. So we have seen that this equality holds. So when n and m are equal, then this integral becomes 2 pi. Otherwise, it's 0. So that's what this means. So it's very concisely expressed. It's nice. So that's all for this video, and in the next video we study another type of convergence of Fourier series, that is convergence in this L2 norm we have studied in this video. See you later. Alright, in this video we look at the Fourier series from a different perspective using kernels. By using a kernel, the partial Fourier sum of a function can be expressed in terms of a simple integral. So let's start. First, let us give the definition of a kernel. So here's the definition. Suppose x is a set, and kernel is a function from x times x. So this is the Cartesian product of x and x from the set of real numbers. And we say this is a kernel function, or sometimes we call it integral kernel, or nucleus, if this function satisfies the following two conditions. First, it is symmetric. That is, k of x, y is equal to k of y and x, where x and y are any elements of the set X. And second is called the positive semi-definiteness. So this, by the way, this is symmetry. And positive semi-definiteness. So this is just like the positive semi-definiteness of a matrix. For any natural number n, and any subset of x, let's say n points from x, x1, x2, and xn, so this is a subset of x. And also a subset of real numbers, so c, c1, c2, and so on, up to cn. These are constants of real numbers. Then we have this sum, double sum, I from I1 to n and j from 1 to n, and ci times cj, or maybe I should write cj later, and kxi xj, and cj is always non-negative. So this is called positive semi-definiteness. So if the function k satisfies these two conditions, then we say this function is a kernel function. That's the definition. I think the symmetry is obvious. It's just symmetric. If we swap x and y, then we still have the same function. And about this positive semi-definiteness, if we consider this as a matrix, like k x1, x1, k x1, x2, and so on, and k x1, xn, and k x2, x1, and so on, and k xn, x1, and k xn, xn. So if we consider this matrix and also consider this as a vector, so like c1 up to cn, and so this is a row vector, and this is c1, c2, and this is a column vector. So this sum is this same as this one. So row vector times this matrix times this column vector, which is greater than or equal to 0. So this is equivalent. So in this sense, this matrix is, we say, positive semi-definite. But the difference between matrix positive definiteness is that we have this inequality for any number of elements here, x, and so this n can be any number, any positive number, integers. So whether this n is 1 or 100 or 10,000, we still have this inequality. Now let's consider the partial Fourier sum. Let's say Sn of x is equal to k from negative n to positive n instead of negative infinity to positive infinity, ck exponential of I kx. And so this is, we define this for some function. So this is actually something like Sn of f of x. That means this Fourier coefficient is determined by the integral of the function f as follows. So let's use that, and k from negative n to positive n, and this ck is 1 over 2 pi integral, and the function an exponential of negative I k y dy. So this is the coefficient ck, and e to the power of I kx. So let's expand this together. So since this is a finite sum, we can switch the order of integral and the sum. So this becomes integral and 1 over 2 pi and the sum. Let's combine this and this exponentials together. We have exponential of I k x minus y, and this function f of y and dy. So everything. Let's write like this. Okay, now let's define this part as this one, dn. So instead of x minus y, let's write theta, 1 over 2 pi and sum k from negative n to n exponential of I k theta. So then this part becomes dn of x minus y. So formally, this partial Fourier sum is written as this: dn x minus y f of y dy. Okay, next let's simplify this function a little bit. So let's expand this summation in the following manner. So multiply both sides by 2 pi. We have 2 pi dn. Just write dn instead of theta, dn of theta for simplification. Then we have exponential of negative I n theta, exponential of negative I n minus 1 theta, and so on, and 1 plus, and so on, and exponential of I n minus 1 theta, exponential of I n theta. And now multiply both sides by exponential of I theta, then we have 2 pi dn exponential of I theta, and we have exponential of negative n minus 1 theta. So this times this is this, right? And next we have n minus 2 here, and so on, and this one corresponds to I theta, and this one corresponds to exponential of I n theta, and the last term becomes I n plus 1 theta. Then subtract the second one from the first one. Then we have 2 pi dn 1 minus exponential of I theta. And so this one cancels this one, and this one cancels the another one. So everything will be cancelled except for the first one minus the last one. Okay, so what remains is this. Negative I n theta minus exponential of positive I n plus 1 theta. Okay, so dn is equal to 1 over 2 pi and this I n plus 1 theta, 1 minus I theta. Now, multiply both sides by negative exponential of I theta over 2. In this way, we can make everything look symmetric. Okay, so if we do this, then we have, let's say, this part becomes exponential, since there's negative sign here. This one comes first, and it becomes I n plus, what is it? Actually should be negative here. Okay, negative. Then that's 1 over 2 theta and minus exponential of negative I n plus 1 theta. Okay, and this one becomes exponential of I theta over 2 minus exponential of negative I theta over 2. Okay, so this is, so that summation, this function can be expressed as this one. Okay, however, using Euler's formula, this can be further simplified. Okay, so we have the same exponent except for the sign. So this is positive, this is negative, but everything else is the same. So that is I sine. So n plus 1 over 2 theta, right? Actually, there is times 2, but that will be cancelled. So this one becomes 2i sine theta over 2. Okay, but these are cancelled, so just write like this. So this is the function dn of theta, which is called Dirichlet kernel. And you should show that, it is an exercise to show that this is indeed a kernel. Okay. Well, actually, kernel should be a function of two variables. So in this case, the kernel x, y should be something like this, dn of x minus y. Okay. So actually, symmetry should be easy to see, because if we swap the variables y and x, then we have dn of y minus x, right? So is this equal to dn of x minus y? So let's look. So if we substitute x minus y to theta, then this is a odd function, and this is an odd function. So odd function divided by odd function becomes an even function. So therefore, it's symmetric. And regarding the positive semi-definiteness, it doesn't look so easy. So what can we do? Well, I don't give the proof here. Maybe I will do another video for that, but it should be a good exercise for you. Anyway, what you should do to prove the positive semi-definite is this. So let x1, x2, and let's say xm be any real numbers, and also c1, c2, and cm be any real numbers. Then for any of these we have, and m can be any natural number, by the way, we have I from 1 to m, and j from 1 to m, and ci, cj, and the Dirichlet kernel dn xi minus xj is always non-negative. So this is what you need to show. Okay. Well, the Dirichlet kernel dn of x minus y, after all, is this 1 over 2 pi and sine n plus 1 over 2 times x minus y over sine x minus y over 2. Okay. Now consider the original integral. So this partial Fourier sum Sn of f of x is, after all, written as this integral. Dirichlet kernel dn of x minus y and f of y dy. Now consider when the case when function f of x is constantly identically equal to 1. Okay, in this case, the Fourier coefficients are all 0, except for when n is equal to 0 and where it is just 1, right? C0 is 1. So if we substitute this, then this is just 1. So in that, and also in this case, Sn of x is equal to 1. It's identically equal to 1. So we have 1 equals to this integral, Dirichlet kernel, and x minus y dy. So the Dirichlet kernel is a kind of normalized function. So if we integrate it from negative pi to pi, it's just 1 for any n. Okay. And if we plot the Dirichlet kernels for different n, we have something like this. When n is equal to 0, it's a constant function. That is actually, from this expression, we can see that the constant is 1 over 2 pi. So this constant, this purple line, is 1 over 2 pi. And when n is equal to 1, we have this green line, which looks like similar to the cosine function, but it's a little bit different one. And when n is equal to 5, we have this turquoise line. So it has more oscillation than the case of n equal to 1. And when n is equal to 20, we have this yellow line. So it's oscillating a lot, but the amplitude is the largest when the difference between x and y is equal to 0. So it is oscillating, but it's damped oscillation. So as the difference between x and y becomes larger, the amplitude of oscillation becomes smaller and smaller. By the way, so we have this partial Fourier sum expressed in terms of the Dirichlet kernel. This one. This form of integral is very common actually, so it has a name for it. So for in general, let's say f and g are periodic functions of period 2 pi, and we say this form of function integral is a convolution of f and g, which is written as f asterisk g of x is defined as this. So f x minus y and g of y dy. So this is y and this is x minus y. So this form of integral is called convolution. And what this means is this. So let's say we have x somewhere here and y somewhere here. So we have a signal at position y. Let's say the signal is given as g of y, and that signal propagates to the point x, propagates to this point through this function, Kernel function in this case, f of y, x minus y. Okay, so something happens at y and that propagates through space to x, and that is mediated by f of x minus y, right? And that effect is uh, integrated for various values of y. So y can be here and integrates from, propagates from here to here, and so on. So from negative pi to pi, we collect all these effects to this point. So that is this convolution. So if we use this notation, then the partial Fourier sum is written as the convolution between the Dirichlet kernel and the function. Next, we consider a different kernel, but before that, consider this problem. Suppose we have a sequence of numbers. Based on this sequence, A0, A1, A2, and so on, we define another sequence that is B0, B1, and so on by this. Bn is defined as 1 over n plus 1 and sum of the first n plus 1 terms, okay, from 0 to n a k. And that is a0, a1, and so on, and an divided by n plus 1. So we take the first n plus 1 terms and take the average of it, and that is Bn. And it is known that if this sequence converges to something, let's say alpha, then this Bn converges also to the same value, but it converges faster than the original sequence. So based on this observation, we define the following partial sum. So we have the partial Fourier sum, S0, S1, and so on. And then based on that, we define sigma n of x as 1 over n plus 1 and sum of these partial Fourier sums as k of x. Now let's expand this using the Dirichlet kernels. So that is k from 0 to n, and this Fourier partial sum is this. Using the Dirichlet kernel dk, we have dk x minus y and f of y dy. Of course, we're assuming some function f. Okay, so this should be really written as sigma n of f bracket of x. Okay. Anyway, so now again, this is a finite sum, so we can switch the order of the sum and the integral freely. So this becomes the integral and this 1 over n plus 1 and the sum, okay, from 0 to n and dk x minus y and f of y dy. So let's write like this. Then if we define this part as fn of x minus y, then again we can write this sum as convolution. between Fn and F. And this function is called the Fourier kernel. Now let's simplify the Fourier kernel. So the definition of Fourier kernel, let's write, instead of x minus y, let's write theta. That is this one. So 1 over n plus 1 and the sum of the Dirichlet kernels. Okay. Now remember the definition of this, not n but k here. N plus 1 and k from 0 to n and 1 over 2 pi sine, what was it? K plus 1 over 2 theta and over sine theta over 2. Now the only factor that contains the index k is this one. Okay, so let's consider the sum of only this part. Okay, so consider this summation. Okay, from 0 to n sine k plus 1 over 2 theta. Okay, let's divide by sine theta over 2 and multiply by the same quantity. So we have sine theta over 2 and the sum sine k plus 1/2 times sine theta over 2. So here we have sine something times sine. So we can use one of the trigonometric identities to make it like this. K from 0 to n. So this can be expressed in terms of the difference between cosines. So that is cosine, what is it? This minus this. So that is k theta, and minus this plus this. That is cosine k plus 1 theta. Right? So if we expand this summation, sine theta over 2, we have the following. So when k is equal to 0, that is cosine 0. Okay, let's write it just everything down. 0 times theta minus cosine theta. And plus, then cosine theta minus cosine 2 theta. Plus, and so on. And finally, we have cosine n theta minus cosine n plus 1 theta. Okay. Okay, so this is just 0. So it's cosine 0 is just 1. Okay. This cosine theta cancels this cosine theta. And this cosine 2 theta is cancelled by the next term, and so on. So everything will be cancelled except for the first term and the last term. So after all, what's left is this. 1 minus cosine n plus 1 theta. Wait a minute. When we use the trigonometric identity, I think we should divide by 2. So everything divided by 2. Let's see. Okay. And again, using the trigonometric identity, so this one can be considered as cosine 0, okay? And this can be written as sine squared n plus 1 over 2 theta, and sine theta over 2. So, putting this back into the definition of the Fourier kernel, we have the following. Fn of theta is equal to sine 1 over 2 pi and sine squared n plus 1 over 2 theta. And wait a minute, we have to divide by this. So this is sine squared theta over 2. And wait a minute, we need to divide also by this one, n plus 1. So let's put n plus 1 here. So we have this. Now you should check that this is indeed a kernel. That is, it should be symmetric and also positive semi-definite. Symmetry is easy to see, and positive semi-definiteness is actually also easy to see once we accept that the Dirichlet kernel is positive semi-definite. So that property is inherited, so to speak, from the Dirichlet kernel. After all, this sum sigma n is just an average of the partial Fourier sum, which can be expressed in terms of the Dirichlet kernel. So if we just expand this summation and apply the positive semi-definiteness to the Dirichlet kernel, and we see that this Fourier kernel is also positive semi-definite. And again, if we apply this transformation to the constant function f of x equal to 1, identically equal to 1, then we have sigma n of f of x is equal to 1 identically. So from that, we see that the integral of the Fourier kernel fn of x minus y dy is also equal to 1. So if we plot Fourier kernels for different n's, we have something like this. So when n is equal to 0, again, it's a constant function that has the value of 1 over 2 pi. And when n is equal to 1, we have this green line here. And when n is equal to 5, we have this turquoise line. So unlike the Dirichlet kernel, the Fourier kernel is always positive or 0. So, but similarly to the Dirichlet kernel, as n increases, we have more oscillations. So when n is equal to 20, we have this. But this oscillation is damped as the difference between x and y increases, just like the Dirichlet kernels. All right, so we now have this sigma n of f of x as the convolution between the Fourier kernel fn x minus y and the function f. So this is the convolution. And now we show this important result. That is, if the function f is a continuous function, then this sequence of functions converges uniformly to the function f. So now we are going to prove this, but what do we need to prove is the following. So we want to prove that this uniform convergence, okay? So what does uniform convergence mean anyway? So let's recall that. That means for any epsilon that is positive, and there exists some natural number n natural number n such that for all x in the interval, in this case it's a periodic function, so let's limit this into this period, and for all n natural number, if n is this lowercase n is greater than or equal to the uppercase n, then the difference between this function sigma n f of x minus f of x is less than epsilon. Okay, the point is the value of this n does not depend on the value of x. Okay, so wherever we evaluate this function, this sequence, this difference becomes arbitrarily small for large enough n. So that's what we need to prove. Okay, so let's start the proof. To begin with, we use the property of the Fourier kernel that it is normalized. So we have this equality. If for any x we have this equality, so the kernel is normalized. So multiply both sides by f of x. So we have f of x and f of x. So it can be put inside because it doesn't contain any y. So we have this. And the definition of the sequence, sigma, let's abbreviate in this way. So the definition of this sequence sigma n is the convolution between Fourier kernel and the function. Okay, so this is y here, this is x here. Okay, so it's different. Now let's take the difference between them, both sides. So we have f of x minus sigma n of x is equal to, so this part is the same, all the integral, this region is the same, so we can factorize and take the difference, f of x minus f of y and dy. And here we should note that this limits of this upper limit and lower limit of this integral can be anything as long as the difference between them is 2 pi, okay, because we are dealing with the functions with period of 2 pi. So for example, this can be from negative pi to positive pi, and it can be from negative pi plus 0.1 to positive pi plus 0.1, and so on, okay? So we have some freedom of choice regarding this range of integration. Now we are assuming that f is continuous in this, is a continuous function with period of 2 pi. So that means f is also continuous in a closed interval between, say, negative pi to pi. So by assumption. So that means f is uniformly continuous. In, let's say, negative pi to pi, but this can be any interval of width of 2 pi, okay? So that means for any epsilon that is positive, there exists some delta that is positive such that if the difference between x and y is less than delta, then the difference between f of x and f of y is less than epsilon, wherever the points x and y are. Now we split this integral into two parts. Okay, so f of x minus sigma n of x is split into two parts, that is I1 and I2. Okay, where I1 is the integral where the difference between x and y is less than delta. And the integrand is the same, fn of x minus y times f of x minus f of y and dy. And I2 is everything else. That is the difference between y and x is greater than or equal to delta and less than or equal to pi, because the range of integration is 2 pi. The difference between the upper limit and lower limit should be 2 pi. So the difference between y and x is limited to this. And since we excluded this part already, so it should be greater than or equal to delta. And the integrand is the same, of course. Now, let's consider the absolute value of I1. Okay, first of all. So by using the triangle inequality for the integral, so the absolute value of I1 is less than or equal to, let's see, the integral, this one is y minus x less than delta. And fn is always non-negative, so we can just take it out as it is. And the absolute value of f of x minus f of y dy. Okay, so this is due to the triangle inequality for integrals. Okay, now we know that f is uniformly continuous. So if the difference between x and y is less than delta, then the difference between f of x and f of y is less than epsilon. Okay, so this is less than f and x, y, and this is epsilon, right? Uniform continuity, uniform continuity. Okay, epsilon is of course just a constant, and so we can take it out, and let's increase the range of integration to pi. Okay, let's include this one. Okay, then this integral is just 1. So this is just epsilon. Okay, so this is equal to 1. And so we have I1 is less than epsilon. And next, consider the case when the difference between x and y is greater than or equal to delta. Okay, and in this case, let's recall the definition of the Fourier kernel. So this theta is x minus y, let's say. So the definition was this: 2n plus 1 pi and sine squared n plus 1 over 2 theta, and sine theta over 2 squared. Okay, so first of all, sine function is always less than or equal to 1. So this is less than or equal to 1 over sine squared theta over 2. And in this case, we're considering theta is greater than or equal to delta. And the sine function is an increasing function of theta here. And as long as, and also we divide by 2, so let's plot this. So sine theta over 2. So let's consider only the positive part. From 0 to pi, it's an increasing function. So let's see, it should look like something like this. Okay, so 1 and 0 here. So it looks like this, but if we squared, then it should look like it's an even function. So it's always increase as the absolute value of delta increases. So the delta is somewhere here, let's say. So the smallest value of sine squared theta over 2 is this one. So that is sine squared delta over 2. Okay, so this is always greater greater than or equal to sine squared of delta over 2. So if we take the reciprocal of it, we have this is less than or equal to 1 over sine delta over 2 squared. So the Fourier kernel is always bounded by this value. Okay, then let m equal to the maximum value of f of y, absolute value of it, when y is bounded by pi, then I2 can be bounded. I2 absolute value is less than or equal to this y minus x is between delta and pi. And the Fourier kernel part, so this is bounded by sine delta over 2 squared. And the maximum value of this is m, so this should be bounded by 2m and dy. So all are constants here. So this is less than or equal to, and we just integrate for all possible values from let's say negative pi to pi. Okay, so then this becomes this times 2 pi, and that is, what is it? 2 pi will be cancelled here, so we have 2m and n plus 1 sine delta over 2 squared. So I2 is also bounded by this value. But we have n in the denominator here, so that means for large, if n is large enough, then I2 can be, the absolute value of I2 can be arbitrarily small, that is less than epsilon, let's say. So putting together, we have this f of x minus sigma n of x is less than 2 epsilon if n is is large enough. So we're done. So this n doesn't depend on this large enough n doesn't depend on where x is located. So that means sigma n converges uniformly to f. And we are done. By the way, previously we have proved the following. So if f is continuously differentiable, so C1 instead of C0, then the Fourier series converges uniformly to the function f, right? But here we prove that if f is just a continuous function, okay, C0, then this sigma n thing converges uniformly to f. So it doesn't have to be differentiable. It just has to be continuous. So there is a difference between this and this. Okay, that's all for this video, and see you later. All right, in this video, we show that the partial Fourier sum of a function, say f, is the best approximator of the function f itself in a certain sense. And using this fact, we show that the difference between the partial Fourier sum and the function f converges to 0 in the sense of the L2 norm. Okay, let's start. All right, so first let's fix some natural number n. And for this n, consider the following set of functions. Phi k of x equals to exponential of I kx. So here k is between negative n, including 0, and positive n. So there are 2n plus 1 functions of this form. Okay. Now, let's define any function as a linear combination of these phi's. Okay. So let's say Vn of x is a function that is expressed in terms of the linear combination gamma k phi k of x, where gamma k is any complex number. Okay, they are coefficients. So this is a linear combination of phi k's. Okay, now what we are going to show is that among all the functions of this form, that is linear combinations of phi k's, the partial Fourier sum, which is also one of these, is the best function in the sense that it approximates well the function f itself. So that is, so Sn is the partial Fourier sum, okay, from negative n to n, and Ck, phi k of x, and Ck here is of course the Fourier coefficient. So that is f of x exponential of negative ikx dx. So if we define the Fourier partial sum like this one, this is the best approximation of the function f, that is f minus Sn. The L2 norm is always less than or equal to f minus Vk. Vk is any function of this form, okay? That is, for all such functions Vk, we have this inequality. And this means that Sn is the best approximator of f itself. Well, actually, we need to impose one condition to f. F must be a continuous function. Okay, so C0. So if this is true, then this is true. Sn is the best approximator. In case you forgot, that the L2 norm means this. So f minus Sn, so this means this, square root, and the integral, and f of x minus Sn of x, and absolute value squared dx. Okay. All right, so let's prove it. Prove. First of all, let's consider this f minus vn squared because we want to get rid of this square root. And this is, so first we add and subtract Sn, and Sn minus Vn here. And this one, if we expand, by the way, this absolute value means the absolute value of complex numbers, okay? We are dealing with complex valued functions, so this becomes f minus Sn squared plus, and this thing squared, Sn minus Vn L2 norm squared plus this times this real part of the inner product Sn f minus Sn and Sn minus Vn inner product. Okay. By the way, in case you forgot what the inner product is, this means this f minus Sn and Sn minus Vn means this f of x minus Sn of x times Sn of x minus Vn of x complex conjugate dx. Okay, so if we expand this inside the integral, inside this integral, there will be this times this, and also the complex conjugate of this and Sn minus Vn. So if we add these two terms, we have only the real part left. That is this one. Okay. However, this part becomes actually 0 because Sn minus, let's say Sn of x minus Vn of x is a linear combination of the exponential function. So that is, to be explicit, this is ck minus gamma k exponential of, let's say phi k of x, right? So this is a linear combination. And so let's say, so we only consider, if we substitute this one into here, then we can split this inner product into the sum of inner products between this term, f minus Sn, and this term. Okay, this is constant, so we can just take it out of the integral. So all we need to consider is this one. Okay. However, this is equal to, so because of the linearity of the inner product, this can be split into f times phi k minus sk times phi k. Okay, but this is actually the definition of the Fourier coefficient. This becomes ck. And this one also becomes ck. 2 pi times ck actually. So this is equal to 0. So we can ignore this part. So after all, we have f minus Vn L2 norm squared is equal to f minus Sn squared plus Sn minus Vn squared. Okay, the norm is always non-negative, so therefore this is greater than or equal to. So let's take this out, and this becomes f minus Sn L2 norm squared. Therefore, we have this inequality, and we are done. And by the way, this equality holds if and only if Vn is equal to Sn. Okay, now let's define the notion of L2 convergence. So definition is here, L2 convergence. Okay, so suppose we have a sequence of functions fn and another function f0, and we say this sequence converges to the function f0 in the L2 norm. Okay, in the L2 norm, this means this definition here. If the difference between fn and f0 converges to 0 as n goes to infinity. Okay, so this is the L2 norm here, the between L2 norm between fn and f0. So this is a real number, non-negative real number. If this converges to 0, then this sequence of functions converges to f0 in the L2 norm. That's the definition. So what does this mean? Remember, this L2 norm is defined in terms of the integral. Okay, so let's write it down here. Fn minus f0. So if this converges to 0, its square also converges to 0. So let's consider the square of it just to get rid of the square root. And so this is fn of x minus f0 of x, absolute value, complex number absolute value, squared dx. Okay, so this converges to 0 means that the difference between these two functions may not be exactly converging to 0 at each point, okay? But as a whole, so this integral converges to 0. It does not mean that at each point fn of x converges to f0 of x. So this may not be the case. So that means at some point they may have different values. But if we integrate the square of the difference, then this integral converges to 0. So that means if there are any difference between the functional values, those contributions may be negligible. Okay, so that's what this L2 convergence means. Okay, let's see an example. Consider the sequence of functions un of x equal to sine pi x to the power of n. And n is 1, 2, 3, and so on. And x is in this open interval between 0 and 1. Okay, note that x is strictly less than 1. So as n goes to infinity, x to the power of n converges to 0, right? So that means un of x converges to sine pi 0, which is 0. And this convergence is at each point. So this is pointwise convergence. So that means if we fix the value of x, then take the limit and go into infinity, then we have this convergence, okay, at each point. However, this convergence is not uniform convergence. Let's see. Okay, so let's say we take xn equal to 1/2 to the power of 1 over n. Okay, then for any n, we have un of xn is equal to sine pi. So this thing to the power of n becomes 1 over 2. So that is always 1. Okay, so that means uh, if n goes to infinity, un of xn is 1. So it's not 0. So this convergence, this pointwise convergence does not imply the uniform convergence. So depending on the value of x, then the limiting value is different. So it's not uniform convergence, not uniform. Next, let's see if this sequence of functions converges in the L2 norm. Okay, so for that, let's calculate this one, the L2 norm squared of this function. So by definition, in this case, actually, the integral should be from 0 to 1 because that's the domain of this function. So this is sine pi x to the power of n squared dx. But sine function is just a real valued function, so we can just use sine squared here. At this point, let's change the variables from x to t. That is, t is equal to x to the power of n, so x is equal to t to the power of 1 over n, and dx is equal to 1 over n, t to the power of 1 over n minus 1 dt. Okay, and when x is 0, t is 0. When x is 1, t is 1. Okay, so this becomes for sine squared pi t to the power t and 1 over n t to the power of 1 over n minus 1 dt. Okay, and at this point, consider this part. Okay, for any theta non-negative, we have this inequality. Sine of theta is less than or equal to theta. If you plot the graph of sine function, it's like this, and it looks like this. And this one is just a straight line, so it's always like this. Okay, so let's use this. Let's put this 1 over n out. And so sine squared is now less than or equal to pi t squared. Okay. Now let's take this pi squared out. And t squared here. Oh, t squared here, and we have t here. So t 1 over n plus 1 dt. And this is easily integrated. Pi squared over 2. And what is it? 1 over 1 over n plus 2. And so this will be t to the power of 1 over n plus 2 from 0 to 1. And this is just 1. So we have pi squared and 1 over n plus 2, which is pi squared and 2n plus 1. And this one converges to 0 as n goes to infinity. Therefore, un minus 0. So this 0 is the constant function, which is equal to 0, converges to 0. Therefore, un converges to 0 in the L2 norm. So converges in L2. So to summarize, this sequence of functions converges pointwise, but it does not converges uniformly, but it does converge in the L2 norm. So we have different notions of convergence, but they may be different. Okay, now we are in a position to prove our goal in this video, that is the L2 convergence of the Fourier series. So here's the theorem. If the function f is a continuous function, c 2 pi 0, then the partial Fourier sum of f converges to f. This is a bit confusing. Converges to f in the L2 norm. Okay, so here the point is c only has to be a continuous function. It doesn't have to be continuously differentiable. Okay. The proof of this theorem is actually quite easy if you understand our previous video. So in the previous video, we introduced the Fourier kernel and Fourier partial sum, that is sigma n of f of x is defined by this. So this is the Fourier kernel, and f of y dy. But this was originally defined as the simple average of the partial Fourier sum. So that is S0 of f of x. So just abbreviate this as S of x. Okay, this is partial Fourier sum, S1, and so on up to Sn divided by n plus 1, because there are n plus 1 partial Fourier sums in the numerator, so we divide by n plus 1. So this is just a linear combination of these those exponential functions, exponential functions, right? So we can use the previous best approximator lemma and the uniform convergence of this Fourier partial sum to f, right? To prove the theorem. So, and we have shown that this sequence of functions converges uniformly to f of x. Okay, and we were assuming that f was continuous. Okay. Now, each of the Fourier sums is a linear combination of these functions, right? Therefore, sigma n of f is a linear combination of these functions too. Okay. Therefore, by the best approximator lemma, we have f minus Sn is less than or equal to f minus sigma n. Okay, sigma n means this, because the partial Fourier sum is the best approximator. So it is better than sigma n in the sense of the L2 norm. But as we have said here, sigma n converges uniformly to f of x. So that means, so the uniform convergence actually implies L2 convergence. So this L2 norm converges to 0 as n goes to infinity. So that means this difference between f and Sn also converges to 0 as n goes to infinity. And we are done. By the way, in case you're wondering why the uniform convergence implies the L2 convergence, let's see this one. So from the uniform convergence, we can say that for any epsilon that is positive, there exists some natural number, capital N, such that for all x in, let's say in this interval, and all natural number, lowercase n, if lowercase n is greater than or equal to the uppercase n, then we have the difference between f of x and sigma n of x is less than epsilon. So this difference can be arbitrarily small. Okay, so this means uniform convergence. Okay, now what about L2 convergence? So L2 convergence means, let's see, so f minus sigma n squared. We have f of x minus sigma n of x squared dx. Okay, so this means if n is large enough, we have this inequality. So that means if n is large enough, then we have at every point, we have this is less than epsilon squared, right? So this is epsilon 2 pi epsilon squared, which is arbitrarily small, because epsilon can be any positive real number. So this can be any small number. So therefore this difference in the norm converges to 0. So in general, uniform convergence implies L2 convergence. But the converse may not be true. Okay, L2 convergence does not, in general, imply the uniform convergence. So let's briefly review our results obtained so far. If f is continuously differentiable, okay, then the partial Fourier sum converges uniformly to f. Okay, and if f is a continuous function, then the partial Fourier sum converges to f in the L2 norm. Okay, and this result can be actually loosened even more. So we can also say, although we don't prove it, if f is just a periodic function that is square integrable, then we can also say the L2 convergence. Okay, that's all for this video. See you later. All right, in this video, we continue our study of Fourier series, and our main question in the study of Fourier series is the following. Given a function, f, we can calculate its Fourier series, and under what condition are they considered to be equal? So for this question, we have so far two answers. One is uniform convergence, and the other is L2 convergence. Okay, uniform convergence means the rate, roughly speaking, the rate of convergence of Fourier series to the function does not depend on where we are in the interval between negative pi and pi. And L2 convergence means the difference between the Fourier series and the function converges to 0 over the entire domain. Okay, so in this sense, these two types of convergence is called global properties. Okay, and in this video, we study yet another type of convergence, that is pointwise convergence. So in this case, we pick each point at a time and study the convergence of the Fourier series to the function. So we don't care about other points when we study the convergence at a given point. So in this sense, this is a local property as opposed to local property, as opposed to the global property. Okay, let's start. By the way, pointwise convergence means the following. So first, we fix a point in the interval. So this is fixed, given and fixed. Then the partial Fourier sum of the function f at this point converges to f of x 0. In this case, we say the Fourier series converges to the function f at x0. Okay, so this is pointwise convergence. So we can consider this as a sequence of numbers. Okay, sequence of actually can be complex numbers. And so S1, Fx0, and S2, Fx0, and so on. So this is just a sequence of numbers. So this sequence of numbers converges to this number. Okay, so this is pointwise convergence. So convergence at x0. So if this holds for each point, then we say the Fourier series converges pointwise to f of x. Well, first we introduce this interesting theorem by Dubois-Raymond without a proof. Dubois-Raymond. Okay, if f is a continuous function, then its Fourier series may not, okay, this is important, converge pointwise. So actually, we don't need continuity of the function for the pointwise convergence. So what do we really need for pointwise convergence? To answer that, we need to define the notion of piecewise continuous and smooth function. Piecewise continuous and smooth functions. So that means this. Consider, of course, we consider periodic function, negative pi to pi, so period of 2 pi, and we make some sub-intervals, let's say gamma 1, gamma 2, and so on, gamma j, and gamma l, let's say. And since it's a periodic function, we consider gamma L here, and gamma L minus 2 pi here. So in each of the subintervals, the function is continuously differentiable. Okay. So the function may not be continuous in the entire interval, but it is continuous in subintervals. This. And gamma 1 somewhere here, gamma 1 plus 2 pi. So that should be something like this. Okay, so each of these are, by the way, these are open intervals. So gamma j minus 1 to gamma j. In each of these open intervals, the function is continuous and differentiable, and continuously differentiable. So such functions are called piecewise, continuous, and smooth. And we can show that this function is actually uniformly continuous on each of these intervals. And for showing pointwise convergence, we need the following lemma, which I give without proof. That is called Riemann-Lebesgue lemma. Okay, so let g of x be a function on an interval between a and b, and assume this is continuous, except for finitely many points. So this can be a discontinuous function, but the point of discontinuity are finite. Okay, and also this is assume that this is absolutely integrable. So that means absolute value of g of x integrated over on this interval is finite. Then we have this integral exponential of I lambda x, and g of x dx converges to 0 as lambda goes to a positive or negative infinity. Now we are ready to prove this theorem. Okay, if f is piecewise continuous and smooth, then for each x0, the Fourier series converges to not f of x0, because at x0 this function may not be continuous. So but this converges to this value, f of x0 minus 0 plus f of x0 plus 0. So what are they? These are actually left limit and the right limit. Okay, f of x0 minus 0 means this: limit x going to x0 minus 0. So this x approaches x0 from the left. Okay, and similarly x0 plus 0 means this the right limit. So x approaches x0 from the right. Okay, so since this is piecewise continuous and smooth, we have something like this. So we have, let's say this is x0. So if this is within the interval, let's say gamma 1 and gamma 2. So if this is inside the interval where this function is continuously differentiable, then this is equal to, of course, this is equal to f of x0. F of x0. But if this x0 happens to be somewhere here, like gamma 2 itself, then so we take the average between this value and this value. Okay, so this may be this function may be discontinuous at this point in gamma 2, let's say. So we take this value as the left limit and this value as the right limit and take the average, and that is the value to which the Fourier series converges. Okay, let's prove this theorem. Okay, so let Sn of x be the partial Fourier sum of f. That is this. Okay, from negative n to positive n, and Cn, and exponential of ikx. Okay, and Cn is of course the Fourier coefficient of f. And now let's use the Dirichlet kernel to express this Sn. So integral from negative pi to pi, Dirichlet kernel of y minus x0, this x0, and f of y dy. And we can shift this upper and lower limits as long as the difference is 2 pi. So let's shift it to x by x0, pi and x0 plus pi, and the result doesn't change. Okay, and let's change variables. So again, the upper and lower bounds are negative pi and pi, but we shift here. So that is dn of y. So shift by x0 to the negative side. So this becomes f of y x plus y, x0 plus y dy. So if the transition from here to here looks not so obvious, then you can just change the variables like this. So instead of y, we use y prime. That is what is it? Y minus x0. Then if y is equal to x0 minus y minus pi, then y prime becomes negative pi, right? And so this would y prime here. And let's see. So when so y is equal to y prime plus x0, so y prime plus x0 is here. And then we split this integral into two parts. That is from negative pi to 0, and we again use y instead of y prime. And from 0 to pi. Now recall that the Dirichlet kernel is an even function. So that means dn of negative y is equal to dn of y. Okay. So using this property, change the variables here. So y to negative pi, then we have from 0 to pi, so we swap the upper bound and lower bound and introduce the negative sign. But from here, we have negative sign also, so that will be cancelled, and we have dn y f of x x0 minus y dy. And this one stays the same. Okay, so let's combine them together. So from 0 to pi, dn we use this property here, and dy and f of x0 minus y plus f of x0 plus y and dy. Now, recall that the Dirichlet kernel is normalized. That means if we integrate the Dirichlet kernel itself by itself, then it is 1. Okay, and it is also even function. So this is actually, if we start from 0, then multiply by 2, we have this. Okay, then to this, we multiply to the both sides this f of x0 minus 0 and f of x0 plus 0. So multiply this one to here and here. And let's switch the sides. And so we have, so if this is multiplied to 1, of course we have this. So this is equal to, and 2 times this thing times this. So 1/2 and 2 will be cancelled, and we have dn of y and f of x0 minus 0 plus f of x0 plus 0 dy. So this is equal to this. Okay, now let's subtract this equation from this equation, this Sn equal to this. So that means Sn of x0 minus 1/2 of f(x0 minus 0 x0 plus 0 is equal to integral dn y. Let's split into two parts. That is f of x0 plus y minus f of x0 minus 0 dy, and plus dn y f of x. Wait a minute. This should be minus here, and plus y minus f of x0 plus 0 dy. So if each of these terms converges to 0, then we are done. Okay, that's sufficient. So let's try to do that. Okay, we put this second one as J1 and the first one as J2, and we show only this one converges to 0. Okay, and this one converges to 0. This can be shown in a similar manner, so we just prove only this one. All right. By assumption, f is piecewise continuous and smooth. So because of this, if we take small enough delta, so there exists a delta, such that for all x in x0, between x0 and x0 plus delta, f prime, the derivative, is bounded. And continuous. Okay, so let's define m delta to be the supremum of the absolute value of f prime, where x is in this interval. And g of y, let's define this function g of y as f of x0 plus y minus f of x0 plus 0. So of course this is the right limit of f at x0. Okay. Okay, then the absolute value of this gy, by the way, y is assumed to be between 0 and delta. Okay, this is ugly. G of y, absolute value, is the integral from 0 to y of f prime of g0 plus t and dt, right? Because, okay, so f prime is the derivative and f g of y is the difference between the function f at this value and this value. So this is it, and this is less than or equal to the integral of the absolute value. This is a consequence of the triangle inequality. But f prime is bounded by m delta, so this is less than or equal to m delta times y, so between 0 and y. So just constant integrated, we get this. Now, let's recall what we wanted to do. Okay, we wanted to do, show that this J1 converges to 0, and J1 is this times Dirichlet kernel. Okay, so what we want to show is this integral gy converges to 0. And in case you don't remember, the Dirichlet kernel, dn of y is this 1 over 2 pi and sine n plus 1 over 2 y here over sine y over 2. Okay, so this one. Now, we next show that, let's see, integral of g of y over sine y over 2, this one, converges. Okay, so this one is less than or equal to, because of this, m delta and y sine y over 2. And it may not be trivial, but when y goes to 0, then this converges to, I think this converges to 2, right? And otherwise, there is no singular point. So this is actually finite. And next, when y is between delta and pi, we consider this integral from delta and pi and g of y over sine y over 2 dy. And for this y, in this range, we have sine y over 2 is greater than sine delta over 2, which is positive, strictly positive actually. So because of this, we have this is less than or equal to, so replace this one with this one, and we have sine delta over 2 and g of y dy. and this is bounded. This is finite. So together with this result, we can say that from 0 to pi, g of y sine y over 2 is finite. And now we apply the Riemann-Lebesgue lemma to this function. Okay, so if we apply the lemma, so exponential of I, instead of any lambda, but we have n plus 1 over 2 and y, and gy over sine y over 2 dy. So this one converges to 0 as n goes to infinity, right? So, but if we take the imaginary part of this whole function, we have exponential. If we expand this into using the Euler's formula and take only the imaginary part, we have sine n plus 1 over 2y and g of y sine y over 2 dy. So this should also converge to 0, right? But this part divided by 1 over 2 divided by 2 pi is the Dirichlet kernel. So that means Dirichlet kernel y and gy dy converges to 0, and we are done. So we know how pointwise convergence is achieved, and if we define a new function, let's say f tilde of x as this, f of x, where if x is a continuous point, and if f is not continuous at x, then we take the average of the right limit and the left limit. If x is a discontinuous point, then the Fourier series converges to f tilde. Fourier series of f tilde converges to f tilde everywhere. So that's all for this video. Let us summarize what we have learned about various convergences. So if f is continuously differentiable, then we have uniform convergence. And if f is square integrable, or actually we didn't prove this, we proved only for the case where f was a continuous function, then we had L2 convergence. And if f is piecewise continuous and smooth function, we have pointwise convergence. Okay, that's all. See you later. All right, we have been studying Fourier series of periodic functions with a period of 2 pi only. So a natural question to ask is, what happens if the period is not 2 pi? So let's say if we have a function of period of 2 pi L, well, L is any positive real number. Okay, then we can define the Fourier series of function f as this. K from negative infinity to positive infinity, and ck is a Fourier coefficient, an exponential of k ikx divided by L. And of course, ck is the Fourier coefficient, and in this case, we define it as 2 pi, 1 over 2 pi L instead of 2 pi, and integrate from negative L pi to L pi. And the function f of x times exponential of negative ikx over L dx. And if we assume f of x is continuously differentiable, then this is actually equal. So in this way, Fourier series can be extended to any periodic functions, not just or with period of 2 pi, but any period. So why does this work? This is just a method of scaling the coordinate system. So if we set y equals to x over L, then replace everything here with y, then we have s of, let's say f of x is f of ly. Let's define this as g of y. Okay, so the Fourier series of g is this. Ck and iky. So this is the Fourier series we have been studying all the way for the period for the functions with period of 2 pi. And in fact, this function g of y has a period of 2 pi because x has f of x has period of 2 pi L, and if we divide that by L, then this function of y has a period of 2 pi. So all of the properties we have proved about the Fourier series for the functions with a period of 2 pi are applicable to functions of any period. Just in case you're wondering what happens to the Fourier coefficient if we replace x with y. So from here we have dy equals to dx over L. So this L and this dx will be replaced with dy, and this will be y. So that is the Fourier coefficient we have. So L pi becomes pi, right? Negative pi, 2 pi, and g of y, and exponential of negative iky dy. So this coefficient is this coefficient, and they are the same, and this expression is the same as we have been studying. So everything is fine. All right, the next question is, what about non-periodic functions? Here we consider a class of functions that are continuously differentiable with bounded support. Support means the set. Support of f is the set, in this case real numbers, such that f of x is not equal to 0. So this is the support, definition of the support, and bounded support means this. So support of f is a subset of some, let's say, constant interval, negative L pi to L pi. Okay, L is any positive real number. Okay, so this support is bounded by this interval. For example, let's try to plot some function. So since this is bounded, so if L is large enough, then all the values of f is 0. Okay, 0. And within some interval, it can take non-zero values. Okay, so this is an example of a function with a bounded support. Now let's calculate the Fourier coefficient of this such function. So ck is 1 over 2 pi L and negative L pi and L pi. Okay, just regarding this function as just pretend this function to be a periodic function with a period of L pi, L to L pi. So we integrate from negative L pi to positive L pi and multiply f of x with exponential of negative I kx over L and dx. Now, since the support is bounded by this, so if we extend these limits to negative or positive infinities, then the integral doesn't change. So we replace with plus minus infinities here. And next, let's define a new function f hat of xi as 1 over square root of 2 pi and integral from negative infinity to positive infinity f of x exponential of negative I xi x dx, where xi is a real variable. Okay, using this, we can express this Fourier coefficient ck as ck is equal to 1 over 2 square root of 2 pi and f hat of wait a minute, k over L and 1 over L. Okay, so this L comes here, and we have 2 pi here in the denominator, so let's take square root of it, and one of the square roots comes here and the other remains here, and this xi is k over L. Okay, so this is an expression of the Fourier coefficient ck in terms of f hat. So now, since we're assuming that the function f is smooth or continuously differentiable, f of x can be expressed as the Fourier series ck and exponential of I kx over L. Okay, now replace this ck with this expression. Okay, then we have 1 over square root of 2 pi and f hat k over L and exponential I, let's write I k over L x and 1 over L. Okay, now let's set xi k as k over L. Then we have xi k plus 1 minus xi k is 1 over L. Okay, so let's write this as delta xi k. Okay, so this becomes 2 pi and summation and f hat psi k and exponential of I psi kx and delta psi k. So this is Can you recognize any pattern? This is a Riemann sum. So if we take the limit L going to infinity, this sum converges to the Riemann integral. Negative infinity to positive infinity, f hat xi exponential of I xi x and d xi. So to summarize, we have f of x represented as a linear combination of infinitely many functions of this form with coefficients of f hat, where f hat xi is this f of x exponential of psi x dx. So this is a generalization of the Fourier series to non-periodic functions or any functions in general. And this is called Fourier transform of f. Oh, this one is Fourier transform, and this one is called the inversion formula. So given a function f, we can calculate its Fourier transform f hat, and from f hat, we can revert the original function f of x using the inverse Fourier transform. Okay, that's it. The further study of Fourier transform is beyond the scope of this lecture, so we stop here. And that's the end of the lecture series on mathematical methods 2. Okay, bye.